All right, so we're on our second day of talking about nesting and crossing and hierarchical models versus crossed factors or whatever type of models. And so what did we talk about last time? Do you remember? So a couple of the key things we talked about. So I've heard from, I'm looking at everybody that I can see right now. Maybe half of you haven't really said anything at all. So this would be a good opportunity to stretch your comfort zone and, get some participation points. You don't have to do it right now, but I'm just saying in general, for those that really are kind of not used to doing it, it's good practice. And I say that from experience. I'm an introvert actually, and I think I probably was pretty quiet in class up until graduate school. Then I started participating quite a bit. But I do want that. I do want to hear from everybody in this class. I think it's important to practice that, and sometimes you need to stretch yourself a little bit. And I think it's good for class dynamics to have not just me talking the whole time. So we started last time, we started talking about nesting and crossing and how those terms, they could mean different things depending on what you're talking about. If you're talking about nested or crossed data versus factors versus designs, they could mean different things. And that's why it's important not to just think about that it just applies to across the board. It depends on what you're talking about. What was the data set that we talked about?
There was like morning, noon, and evening across 3 days, and we were trying to decide.
So that was one of them. That was the hypothetical data set where, the question was, do morning, noon, and evening mean the same thing across days? And it's important to, in your design, to think about whether they have consistent meanings. And that may indicate whether you have nested factors or cross factors. That's one big thing that we talked about. We also talked about anything else you remember?
The study that looked at air pollution and weather on children with asthma.
Yeah, so we talked about the Koonsberg study and how we can use hierarchical models to actually test for independence, whether, we had siblings in the study. And the question is that dependence, the potential dependence between the siblings, going to affect our results? And so one way to test for the correlation that there might be between siblings was to build a hierarchical model and then test the model with and without the family level random intercept. And that's one way to do it. That's not the only way, but that's one, pretty straightforward way to test for correlation. And we found that dependence wasn't so strong that it created a better model, that the model without the family intercept actually had a better AIC. And that may have been partially due to the fact that there weren't a lot of siblings in the data set. It was a minority of cases where, you had siblings. So that's something that's an approach that you can use in general. Like if you have that same issue, you may have siblings, or there may be some other way that you can identify potential correlation that you can test for by building a hierarchical model like that. So those were two of the big things we talked about last time. And we're going to continue on today with hierarchical models. And here's a study that this was done, this data set I got maybe 10 or 12 years ago, I had a graduate student I worked with, and then they came to me with this data set, and we talked about how we could analyze it. And so what happened was with the study was they implant tumors in mice, and then they watch over time to see how the size of that tumor changes. And what's interesting is there's treatment and control. You might usually think that a treatment is going to try to eliminate the tumor, but in this case, actually the two treatments, A and B treatments, were designed to actually keep the tumor bigger. So it maintained the size of the tumor, whereas the control was actually the one where if you implant the tumor and there's no real treatment, then it's just going to shrink and go away. So the purpose of the treatments was to see if it could maintain the size of the tumor. And I don't know why that would be of interest, like down the road clinically. I'm sure there's a reason, but that's the experiment they're doing. And so in this case, we have mice, and then we have tumors within mice, and then we have repeated measures over time. So it's 3-level data. So so again, you can think of the level 3. That's the number is the biggest, right? And that's associated with the biggest experimental unit, and that's the mouse in this case. And then we have tumors within mice, and then repeated measures. So 3-level data, kind of similar to the last example we had, you know, where we had 3-level data and then repeated measures was the smallest level to it. So, so like I mentioned, that treatments A and B tended to actually maintain the tumor size, while those in control tend to have tumors shrink over time. But we want to know if the treatment really makes a significant difference. You know, that's usually what we do in statistics is we're testing for differences there. One of the issues with this data set, though, was that it was explained to me like through somebody else and not through the PI, the design of the experiment. So this can have a big impact on how we do the analysis. So I wasn't sure whether there was a systematic way that the tumors were placed within mice. For example, maybe they put tumor 1 on the left side and tumor 2 on the right. Or, you know, they put a tumor in one part of the body, you know, the back, and then one in the front or the head or something like that. That wasn't described to me. And what, you know, that makes it fairly difficult, because then we're not sure if the factors are nested or crossed. If they do a systematic approach, if they say left and right, for example, we could say we could do a cross situation like this. Now, so that's the so if the tumors were placed systematically, you might have a situation like this, and then you could consider those cross factors, right? But if they're just kind of placed in random spots in the mouse and it's not consistent across mice, then it may be a nested situation where the tumor is nested within the mouse. So so that, again, that's not described, that was not described to me. So let's think about, you know, if you don't know, like, what are some possible ways to analyze the data? So the first approach that I'm going to describe where we consider tumors nested within mice. And so we're going to have nested random intercepts, plus an error covariance structure to account for repeated measures over time. And we talked about this last time, how including a random effect at one level will induce correlation between units on the next lower level, right? So if we include random effects for mouse and tumor, we have modeled correlation between tumors and between times. However, we go ahead and we add in the AR1 structure because this is a pretty simplistic correlation structure between times, where you're just saying, you assume the same correlation regardless of the distance between the time points. And that's one of the main reasons why we add on the AR1 structure. The AR2, the approach 2 is where we assume that tumors were placed systematically within mice, so that tumor and time can be considered cross factors. And we can use the chronic product structure in that case. Okay, so we have two main approaches here to analyze the data. But what I'm going to actually show you is that even if tumors and times were not crossed, approach 2 yields a reasonable covariance structure for Y, and I'll show that more in a little bit. Okay. So final analyses were performed on log transformed tumor volumes for two reasons. First, log volumes are more log normally distributed, and so volumes were log normally distributed, or log volumes were normally distributed. And the other reason were that results were not as sensitive to model specifications with that approach. So things that you normally, as a statistician, you need to kind of look for every time, regardless of the modeling approach you're doing, is the outcome, what is the best distribution for it? Do I need to log transform it? Those are things that we normally just check for. And if you have a predictor that's really skewed, that's non-normal, do you need to worry about transformation in that case? I saw one or two say no. What are the things you need to think about for a predictor that has a weird distribution?
I would say how influential the outliers are.
Yeah, I would agree. So, and Chloe, I saw you shake your head no. I would agree that you don't have the same issues in terms of checking the distribution. Like, it doesn't have to be normally distributed, like we have to look for the outcome. But that's the thing you might be concerned about is for a skewed distribution, is the tail of the distribution going to have undue influence on the estimate? So that's more why you would consider, log transforming a predictor. But we don't check it in the same way that we check the outcome, the distribution of the outcome. There's other types of transformations, but honestly, like in practice, right skewed distributions are probably the most common non-normal distributions. And a lot of times you can log transform, like a natural log transform, and there's nice properties with that. Because then when you exponentiate, then you have a relative increase interpretation, which is kind of nice. Okay, so I'm gonna walk through the analyses for these two approaches with this data set. And just to simplify notation, I'm going to consider 3 repeated measures, but there are actually 5, so that's just to show you what the matrices look like in a easier way to digest it. So the code, and you could easily do this in R as well. But for the nested approach, we have, so we have mouse, that's the largest unit, and then tumor within mouse. You can not worry about this. Mouse, yeah, don't worry about that. I'll just scratch that out within mouse. The actual variable name was mouse, NO as for mouse number, but that's kind of confusing here, so don't worry about it. Okay, so we have nested random intercepts, and then we add the AR1 structure for repeated measures over time. Okay, so this is the code for the nested approach. And then for the Kronecker product, we have just a repeated statement, and then we have considering the mouse as a unit, we have repeated measures because of the tumor that's placed within the mouse. There's 2 tumors placed within the mouse. And then we have repeated measures over time. So again, this is going to be a situation where it would make sense if you had something like left-right tumor and then mouse, that situation that I just drew out in a cross fashion. So this is where this would make sense, this approach. Okay, so that's the code that we have. This is just expressing the model. We have the random intercept for mouse and then tumor within mouse, and our usual assumptions for the mixed model. This is a part that is going to be, you want to pay attention to a little bit because you have a homework question like this. Write out the design matrix for the random effects for largest unit and for the full data. And that's the resulting V matrix.
I have a question on just sort of the general concept of nesting, because so nesting sound to me, a lot of this longitudinal data sounds nested, right? You could say times are nested within subject. Yeah. But is there a very specific definition of nesting where it's more of a hospital level thing where one patient wouldn't go to 2 hospitals, so that's why it's nested? I guess that's the first.
Yeah, I understand. That's a really good question. So we talked about last time how nesting and crossing, that's exactly why I define it differently depending on whether you're talking about data or factors or design. I distinguish those because sometimes it's not clear cut. Sometimes it is clear cut, like you said, a patient going to one hospital or a teacher in one classroom. Sometimes it's more straightforward. Other times like this, if they're randomly placing tumors within mice versus putting them systematically, that's kind of not as clear. But that's why it's important, I think, that we distinguish whether we're talking about the data or the factors and so forth. So okay. To answer your question, yeah, in some cases it's more straightforward. In some cases, it's hopefully more straightforward if we're talking about a specific issue like the factors or the data itself. That's just sort of how it is. So I think we can keep talking about more examples, maybe to keep illustrating the difference between those. So the
can I piggyback on that?
Sorry?
Can I piggyback on that question?
Yeah, sure.
When you have nesting at the design level, are you kind of obligated to put that into your model, whether it improves your fit or not? Or, I mean, I feel like it's one thing if it's the factors, you can kind of make a model choice of what fits better, but when it comes to the design side, is it kind of like, when you're modeling things and there's just certain covariates you have to put in your model if you ever want to, get it accepted anywhere? Is it kind of like that with the design side of nesting, where you just have to do it?
Yeah, that's a really good question, and that we're going to kind of talk about that in these slides. But basically, my suggestion is, yeah, you should, if your design has nesting, then you should do that in your model. Like your model should be based on the design, really, and not just based on how well it fits. That's my main answer. But what I'm actually going to show you today is, like, there may be situations where um, using a cross versus nested approach not only depends on the design in a conceptual sense, but also what makes sense in terms of the resulting covariance structure. So that's maybe a complicated way to say it depends, but I would say in general, yeah, you have your design, and then your model should follow from that in most cases. But what I'm going to talk about here are some exceptions that you can think about to that rule. So this is kind of a good data set for discussion. And with this specific example, like it wasn't clear to me whether the factors were nested or crossed. And like, if I was going to actually write a paper, I would definitely go talk to the PI and say, look, I need to understand what you did, and not just assume, okay, one thing or the other. But again, what I'm going to talk about is there are some other reasons that we might consider choosing a nested or cross design for our analysis. Okay, and I'll get to that here in a second. So, so for practice, write out the design matrix for random effects for the largest unit, mouse. Let's see if I can do that. I didn't do this before, so you may have to help me here. So we have Z sub H, and we know that we're going to have a left bracket and a right bracket. Right? So those are two things that we know for sure we're going to have, right? There's probably going to be ones and zeros in there, right? For a Z matrix. You guys know how we should start this? We have two random effects that we need to be concerned about. We have the mouse, and then we have the tumor within mouse. I'll let you guys think about it for just a second. Let me pull something up real quick. That's not something I'm going to show you right now, but this gives me something to look at. Right. So for one mouse, we have that one mouse. We're going to have the first column is going to be ones, okay, because they're going to have the same. You can think of. I'm just going to. Come down just a little bit with this. The first column is going to relate to B sub H, so I'll just write that above so that we know what we're talking about. And then the next two columns are going to relate to the B1H, and B2H. Okay, so maybe that'll help kind of give you a sense. So what should we put in that first column? We're thinking about one specific mouse. So you can think of, you know, H, in this case, maybe H is 1.
So that one is just constant across all measures?
Yeah, yeah. So we would just, for that one, we just have a column
Like
of,
just put a 1 for all of the rows?
exactly. So we have a 1 here, and that'll just be a column of 1s. So the question is, how many do we have? We have, so we have 2 tumors, right? And we have, let's say, again, let's say we have 3 repeated measures here. So how many rows should we have in this?
6.
6? I think 6. I think you're right. So we have, we'll have 6 of these, right? What about for the second column here? So this is going to identify the first tumor, right? It's going to have a random intercept for the first tumor.
Would that be 3 1s and then 3 zeros in the first column?
Yes. So we have 3 1s and then 3 zeros, and then similarly in the, you know, flipped around though, we have the zeros here, and then we have the 1s here. Okay. So this is the Z matrix for one mouse, right? And then you can build the complete data Z matrix by putting these down the diagonal, essentially. Okay, so this is a way that we design the Z matrix for nested factors when we have nested random intercepts. Okay, so fairly straightforward.
Hey, Matt.
Yeah.
This question might be kind of silly, but we talked a lot about like less than full rank models for fixed effects. Do you ever have to worry about those with random effects?
Yeah, that's actually a really good question. My short answer is you don't. But that's a really good question. We don't have to worry about that. And obviously, there's dependence here, right? In this Z matrix, because the second 2 columns add up to the first one. But that's a good question, and I'll come back with an answer. But the short answer right now is that we don't have to worry about that. So what you do to get the V matrix here is we can take our ZG, Z transpose plus R, but we're dealing with that that mouse level matrix. So this would be, let's make sure that we get the right dimensions here. So how do we get this one here? This R matrix. That's interesting, right? Because we have 6 repeated measures. So we know that we have this V matrix is 6 by 6, right? And our Z, that's a 6 by 3. That means that this G matrix, that's going to have to be a 3 by 3. And we have this Z, this transpose is going to be 3 by 6, right? So that works out. And here we have a 6 by 6. So how do we get this thing, right? Because the R matrix is just for the repeated measures. So the way we get that is R sub H, we're going to have, I'll call it RIH here, and I'll just say 1H and 2H here, and then off will be zeros. So this thing is a 3x3. This thing's a 3x3. This is a 3x3 matrix of zeros, and this is a 3x3 matrix of zeros. So R I sub H, that's going to have that usual AR1 look to it for the 3 repeated measures that we have. But you do it within separately for each tumor. Actually, down here I used phi. Sorry, I'm going to back up just a little bit here, just to make sure that we have the same symbol, so it's not too confusing. So we have phi squared, like that. So I stay consistent, and okay, that's a 2 there. I'm gonna not fight that one right now. So does that make sense? So what we've done is we created a correlation matrix, and you can look at this and separate it into pieces. And so here, this piece right here would be the correlation matrix for tumor 1, and then this would be the correlation matrix for tumor 2. And then this would be between tumors. And you can see that it's a pretty simple correlation matrix. It's just saying that, you know, regardless of time points, you have the same covariance estimate between the tumors. Okay, by including these nested random intercepts. So this is the question that I had when I looked at this. I was like, okay, so within a tumor, we're allowing a decay in the correlation or the covariance as you increase the time between measurements. Well, why don't we have that in the off diagonal? Like, even if you're looking at you know, between tumor 1 and tumor 2, it seems like the correlation should decay as you spread out the time points, but we don't get that when we do the random intercept approach. And that's the whole reason why conceptually, that was a consideration of mine, was that when we use the Kronecker product, we are going to get that decay. And I'll show you that here in a second. But that's why, to me, intuitively, even if the factors are nested, to me, it kind of made sense to in the off diagonal that we'd have a decay in the correlation as well. Okay, so let's look at that.
Matt, can I ask a follow-up question before we move on?
Yeah.
Yeah, so I was wondering how this looks if there's missing data. So I guess that's similar to one of our homework questions, but if, you know, one of the tumors, like say one mouse only had one tumor as opposed to 2, or we didn't have the ability to collect the second tumor data.
Okay. Then the size of those matrices may change. It may, like if you just have one measure, then you can make the size of the matrix correspond to that.
So if 2 of the 3 mice, say, had all their measures, but one mouse was missing measures, would that have to reduce down the dimensions of the
Yeah,
entire matrix?
it should work fine because you when you build that the complete data structures, you can have different sizes, you can have different dimensions to those individual mouse matrices, and that'll be fine when you build your complete data structure. They don't have to all be the same size. Good question. So fitting this structure, and if you request the V, like if you in your random statement, if you after the slash you put V or V core in there, in this case V core. So we got this from using the V core. This is the numerical version of this structure that I wrote here, and you're going to do the same thing for your homework questions. That's kind of similar to what I've done here. You kind of write out theoretically what it looks like, and then you can get the numerical fit for it to see what that looks like. You can see that the correlation is fairly weak between tumors, regardless of which 2 time points you're considering. And these are the specific covariance parameter estimates. You can see the AR1, the phi is about 1/2, the day-to-day correlation between the measures. And you can see that the residual variance is a lot bigger than the tumor and the mouse variances. The mouse is pretty small. So that's what they say, right? The mice are pretty genetically homogeneous, and that's one of the reasons why they like to use mice for a lot of these experiments. So the second approach, we have the Kronecker product structure. And if that's the design that was used, this is what I would use for sure in this case. And so we have the 2 tumors. So you can think of this, maybe it was left and right. If that's the case, that would be the structure that would make sense there. And then for the 3 times, we have the AR1 structure. And if you cross those, the resulting structure is here. And so we get a fairly complicated, flexible structure that only requires 4 parameters. You see 5, but this will fall out. The sigma squared epsilon actually falls out. So we have 3 there plus the correlation. That's why the Kronecker product is a beautiful thing, because it's fairly flexible, but it doesn't require a lot of parameters in it. But it's made for crossed factors. Okay, so again, we have the situation, you can kind of think of it this way. This is tumor 1 here. Get rid of this thing. And then we have, this is tumor 2. And then this one is going to be between the 2 tumors. And so, for example, and what do we have here? We have time. So we have time 1, 2, and 3, time 1, 2, and 3, and the same across. So for example, this one right here would be, that's the covariance between tumor 1 time 1 and tumor 2 time 3, right? Did I do that right? Guys with me? Need to double check what I'm doing because sometimes it's that looks right. So what we're allowing here in this off diagonal is a decay in the correlation as you're increasing the distance between time points. And that's why, to me, it's like, why would you have the same correlation? You know, just because you're talking about different tumors, I would think there would still be a decay in the correlation as you spread the times apart more. And so regardless of whether it's nested or crossed, I think this leads to a little bit of an intuitive structure, more intuitive than the nested one. And this is what it looks like numerically if you ask for it. And so here we get the, this comes by using the R core option in the repeated statement. And Jonathan's going to give me the Kronecker product for R. He says it's easy, right? So you're going to do that, and I'll be really happy because no one, I've had people send me, here's the Kronecker function or the package, but not the specific, here's the 3 or 4 lines to actually fit it. So that'll be really good, Jonathan, if you can do that. So this is the numerical one, and again, in this case, this is the actual five measures over time. So we can break it down this way. And so this would be for tumor 1 over here. This would be tumor 2. And then this would be between the 2 tumors. Okay. So the question is, what fits better? We got it. The AIC here was a 188.1, and for the nested approach was pretty close. Okay. Now I'm not telling you like the reason I'm showing you this is not to say that you should pick based on AIC. You should generally, I think you should pick based on the design. What is appropriate for the design? But the other thing I'm telling you is there may be things to consider more than just the design. In this case, the correlation structure to me is more intuitive using the cross factors than the nested one, even if the factors are nested. I'm not saying that that's why you should go with that approach. But if we don't know, we in this case, we don't know which one actually was used. But the AIC actually was a little better for the cross factors, not by much, but they have the same number of covariance parameters. So there's not a simpler model. So it's not like, well, this one's has fewer parameters, so let's go with it. This is a head-to-head comparison, and the Kronecker product had a slightly better AIC. So the one thing though, we used the unstructure here, right, for the tumors. The one thing that you could do if they were nested, would there be a reason to believe that the variance for the first and second tumors placed in the mouse would be different if they're randomly placed in there? I don't think so. So that's one way you could modify this, is to, if it were available, you could try a CS structure instead of the unstructure for the tumors. if, you know, if that nested design was actually used. So some of the talking points here, I'll get to in a second.
So
But
Matt,
yeah,
I have a silly question based on, you mentioned 5 measures, and I was wondering, in the structure up, in the variance structure, we have like 6 by 6.
yeah. So that's a good point. So the reason why that is in these examples, I used 3 repeated measures here. And we have 2 tumors, so that's how we get the 6. So we got 3 by 2 equals 6. The actual data has 5 repeated measures, and that's why we end up with a 10 by 10.
Okay.
Yeah. And I did that just for ease of, you know, writing stuff out. So actual data has 5 repeated measures. And so we would have 5 by 2, so 2 tumors, 5 repeated measures. So that gives us our 10. That gives us our 10 by 10 for the actual data. So the code we write for this, if we're doing the cross factors, you have your, you know, your Kronecker product. So again, you list the Kronecker product choices that we have are the un by AR1, un by CS, and un by un. Those are the 3 that we can do in SAS. If we can do it in R, my guess is that we might actually have even more flexibility, because you may have to write out the structures. I don't know. I'm waiting for Jonathan, eagerly waiting for that to see. That'll be a nice addition, especially if we want to do a structure that goes beyond those 3. So tumor, we know that we're gonna do the unstructure for that. So that relates to that one, and then day relates to the AR1. So the first one you write over on the left side is going to be the unstructure. The right one's going to be the AR1, and similar for the other structures that you could model it with. I have some estimate statements that I've added, and these are basically comparisons at the last day for 2 of the 3 groups. So control versus treatment at day 18, control versus, the first one was treatment A, control versus treatment B is the second one at day 18. And then some different contrasts. And this is actually maybe worth talking about a little bit. You actually had a homework question like this, where I asked you about polynomial trends in the data, and it was just for time in that case. And so in this case is day. So for 5 time points, a linear contrast would be -2, -1, 0, 1, 2. And then you can write similar contrast for quadratic, cubic, and quartic. But I want to distinguish the main effect polynomial trends versus the interaction polynomial trends. So the main effects for time are essentially averaging over group. As a whole, is there a linear trend in the data? Is there a quadratic trend in the data? Is there a cubic trend in the data? That's what these tests up here. What these ones test are, is there a linear by linear interaction? Is there a quadratic by quadratic interaction? And so forth. So I think it's worth a few minutes here just illustrating some examples. So if we have, let's say for 2 groups, if we had 2 groups, what linear by linear interaction is saying specifically, like we have an overall test for interaction, right? Any type of interaction. That's what we get when we do the group by day. So that tests for any kind of interaction. But we're breaking down that total interaction into different types. And we're asking specifically, is there a linear by linear interaction, quadratic by quadratic interaction, and so forth? So you create a linear trend for one group, and you see if that's different than the other one. So that's testing, you know, something like this. There would be that would be linear by linear interaction. I'll show you a quadratic one where there's a quadratic by quadratic interaction, but not linear interaction. So like if we had, like for the dog data, we had a trend like this, right? For one group, and for the control, it was essentially flat. Is there quadratic interaction there? Well, what you're doing is you're testing the quadratic trend for one group and comparing that to the quadratic trend of the other group. So there is quadratic by quadratic interaction. So specifically, this group has no quadratic trend, and this group has quadratic trend. So there is quadratic by quadratic interaction. Now we think about, see if I can think of another one here that's where you have one but not the other. Obviously here you don't have no quadratic by quadratic for that example.
Would the first one be yes? Would the linear by linear be, like, would you find that significant because they're different slopes, or just because, or no, because they're just both linear?
Great question. That doesn't tell us if it's significant. So let's say these are, it depends on what you're talking about. If this is from sample data, you need to test to see if that difference that you observed is significant or not. If this is for the populations, then yes, then you just look and see if the lines are different from each other. Does that
The
make
test
sense?
is just saying, yes, the test of linear by linear trends and the interaction is just telling you that they're both linear. It doesn't tell you anything about, like,
the test is for a difference in linear trends between one group and the other group. So what I've drawn here, let's say these are for the population. So any difference that you see, there's an interaction. So the fact that the slope, the lines aren't parallel to each other, then there's linear by linear interaction. So another example, this is one where I'll draw a couple more. So that one there, and let's say we had this situation. So the overall, if you were to average these out, right, you get something like this. So this would be an example. I don't know, maybe this helps answer your question, Carrie. So there is no overall linear trend, but there is linear by linear interaction. Okay. What about this one here, where obviously there is each group has a quadratic trend to it. So think about the main effect, the overall test for quadratic trend, main effect of quadratic trend, and the interaction. Is there, if you were to average those out, would you get a quadratic trend?
Yeah.
Benjamin, yes, right. So, so it like the average of these would be like something like that, right? So yes, there is an overall quadratic trend. So that's the question, quadratic trend here. Overall, yes. Quadratic by quadratic. In other words, we're looking at the quadratic trend in one group compared to the other group. No, there's not. Because if you were to measure that quadratic trend, you might get a 3 or something positive for the first group. But it's the same for the second group, it's just shifted down, right? So there's no quadratic by quadratic trend there. But the overall, if you're just looking at overall, the trend combined for the groups, there is. So that's kind of some examples. And this is an aside. So this is an aside from the data.
Quick question. So under what circumstance can we deduce an interaction, but the lines are actually not crossing? I came across a paper where, for example, in the linear and linear, the lines were not crossing, but the conclusion is that there's an interaction. So I've come across several cases where the lines are actually not crossing, but they conclude an interaction.
Yeah, so, and that, yeah, so they don't have to cross for interaction. The thing that you're looking for is whether the lines are parallel or not. So, you know, if you had a situation like this, there's still linear by linear interaction. Yes, in that case.
Okay.
Yeah, good question. So I did those tests up here for this tumor data, and you know, both the main effects for those polynomial trends, and then the interaction, the polynomial interactions. So again, for each group, you can think of actually getting a numeric value for the linear trend, for the quadratic trend, cubic, and so forth. And the interactions are comparing that quantitative value of one group versus another. Here, I'm actually comparing all three with each other. So I need 2 rows in those C matrices to do that. Okay. And just running forward a little bit, let's look at the plot of the points. So the 2 treatment groups, we see here relatively flat. So the treatment was doing what they hoped. It's maintaining the tumor size. It's maybe decreasing a little bit, but not a lot. Whereas the control group, so here's control, and these are the 2 treatments. Based on what you see, what kind of polynomial trends and interactions appear to be there? Obviously, whether they're significant or not depends on the amount of variability here, right? Like the question is, we see a little bit of change here from a straight line, but is it really enough to say that they're, is that a cubic trend? Because there's two changes, right? It's kind of flatter and then it's steeper and then it's flatter. That suggests a cubic trend, but is it really significant? We have to look at the data and the standard errors to assess that. And the same thing here. This group, there's kind of it rises up just a little bit and then drops and then goes flat. And this one dips a little bit and then comes back up. Are those really significant? So that's what the tests are going to tell us. So if we go back to those estimates, we can see that there's a strong linear trend, and this is the overall one. So what is that overall linear trend in the data?
That's averaging across all the groups.
It's averaging across the groups. In what direction would it be going?
Top left to down right?
Yes. So we'd be starting here and we'd be going this way. Whoops, not quite that strong. Kind of like that, maybe. That's that, averaging over the three groups. And it's really the control group that's driving it. The other two groups are dropping a little bit, but it's really the control group, I think, is what's making it so significant. Okay, we get this strong, really high test statistic and strong p-value. We see that we actually have a little bit of a cubic trend. I'm not sure you'd be able to. I think it may be that it's flatter initially and then it drops and then flatter. Even if you average over groups, I think that's probably what's happening. And that's why we see a marginally significant cubic trend overall. The linear by linear is significant. And again, if you look at this, what's causing that? It's really the control group, the linear trend for the control group versus the linear trend in the other two groups, I think is driving that linear by linear interaction. But we don't see any other trends that are significant, at least in the interactions. Yeah, these are all non-significant. Okay, and then we have tests at day 18, specific tests versus comparing the control versus each of the treatments, and then the treatments to each other. This one is a little surprising. I'm gonna have to check that one because it doesn't seem like they're that different. At day 18, which is over here. So I'm just gonna
that one makes sense because it's the control versus the average of treatment A and B.
Oh yeah, you're right. I didn't read that correct. You're right, Carrie. That's why that is. That's why I need help from you guys sometimes. So for that test, we're comparing the average, which is going to be about right there. We're comparing that to that, right? And that's pretty far away. So yeah, thanks. So how do they actually measure the tumors in these mice over time? I'm thinking that they have like a little CT scanner, and they put the mouse on a little bed and they lie him on his back. And do you think I don't know, honestly, I don't know how they do it. That we have repeated measures over time. So they're not killing the mouse, right, to measure it. They're doing something humane to actually measure the tumor. I don't know how that works, but I'll be curious to learn how they actually measure the size of the tumors there. Any questions that you guys have on, so we've done a lot here. We've talked about nesting and crossing and how you analyze data and how that matches either the design or maybe what you think intuitively makes sense for the covariance structure. We've talked about polynomial trends. We talked about polynomial interactions, a fair amount that we've gone through. Any questions you guys have through that?
I have a quick question about the polynomial trends.
Yeah.
Do you have like a scientific basis to model those, or do you just do it naturally just to check? It seems like a lot of these examples we use polynomial trends, and I'm not sure if it's because we just fit it because we can, or if we have like evidence that suggests we should.
I think that's a really good question. I feel like, you know, if you're doing exploratory analysis, you know, that would suggest maybe it's okay to just kind of start exploring. But I really, for most, you know, research that you do, like you write a grant, you should establish up front that you want to look at certain things. And polynomial trends might be one of those things that you look at. If there's a certain number of time points, obviously that's going to indicate how, you know, the degree to which you can, what degree of polynomial you can look at. You know, if you have 4 time points, you can't go beyond cubic polynomials. But I think your question is good because, like, if you have specific research questions, I don't think you should necessarily be just, you know, examining everything necessarily. You should have in your mind, you know, I want to look at this or that, and it might include looking at polynomial trends. But the way I've kind of presented it here is it looks kind of like exploratory research, right? Because we're just trying to understand the nature of how these treatments and application of treatments affect measurements over time and the mean response. So I think that's an important point, that really we probably should establish that, you know, we want to look at polynomial trends. You don't necessarily have to look up to the 4th degree. You know, we do that here, and we can do it because we had 5 time points. So that allows us to do it. But you don't necessarily have to look up to the quartic. You could just say, I want to test for linear and quadratic. And that's all I'm really concerned about. So again, I think you can lay that out, you know, in your research questions ahead of time.
Can I ask a follow-up to that?
Yeah.
We have 11 tests right here. When do you start worrying about like multiple comparisons and stuff?
Yeah, that's a good question as well. The biggest time I start using multiple comparison approaches to modify p-values and so forth is when you have multiple groups and you're looking at, you know, all pairwise comparisons between those. That's usually when I do it. I don't typically apply multiple comparison approaches like in a situation like this, especially if I've laid out in advance. I want to look at polynomial trends to understand the data. It could be that your main tests are these comparisons at day 18, right? Between, you know, to see if the treatments work essentially. And you can say that, you can say, these are my main tests. And then you can say, well, I also just want to understand the patterns over time. And to do that, I'm going to do polynomial tests. And so by stating that, you know, here's your primary test and here's your secondary test, that's sort of an alternative way, an alternative to doing multiple comparisons. I think no matter what you do, whether you decide you want to control for multiple tests or not, the most important thing is to state the number of tests that you did. Like if you write a paper, be straightforward and say, we ran these tests. And don't just state the ones that were significant, state all the tests you did, because even if you don't apply a multiple comparison approach, the reviewer will have some idea of if they were to do that, you know, would certain things stay significant or not. So I think no matter what you do in terms of, you know, controlling for multiple comparisons, at least give the reader a sense of how many tests you did. The last thing that we have in these slide set is, well, really, I think I'm going to wait on that. I'm looking at the time that we have, and there's a good cut point here. And what I'd rather do is just kind of highlight, you know, going back to this, the mouse and tumor data and how we model it. You know, just a summary of the points. I talked about this one already, that if we had this structure available, I think I might try it if I knew that we had nested data. I think I would probably try that one, because I don't think we need to estimate the variances uniquely if they're just randomly putting the tumors within mice. Based on some follow-up discussion that I've had with people that are doing experiments like this, I think that the tumors were probably placed systematically in the mice. And so I don't know for sure, but my guess is that both the design and what's intuitive about the covariance structure would suggest using the crossed analysis approach for these data. So one of my points is, in general, I would recommend that you stick with the model that is consistent with the design unless there is good reason to change. For this study, we were not completely sure of the design at the time that I did the analysis. If we're going to, you know, if this was going to be a published paper, I would talk to the PI for sure and try to really figure out what it was. Approach 2, which was this was the Kronecker product approach, yields a reasonable structure that's also intuitive, even if the tumors were not systematically placed within mice. So there was an advantage to it, even if the design was nested, in my opinion. So there, you know, in general, when you model data, there is some judgment involved. There is some subjectivity. You get numerical, you know, goodness of fit scores. You get AICs, things like that you can use to help you. But there is some judgment that you're going to use in creating models as well. Okay, that's how things go, and it kind of makes it fun, right? It's not always clear cut. What we can talk about next time is crossover designs for repeated measures data. So I'll take just maybe 10 or 15 minutes at the beginning of the next lecture to talk about this. Actually, yeah, I have to figure out what I want to do, because the piecewise regression, that stuff is really cool, and there's a lot of slides there as well. So I may have to make one of these things read on your own time type of thing. I'll have to figure that out, because I have one lecture to do, and then Gary's going to come in and do some guest lectures. I just don't want to start this right now because we just have a couple minutes left. But if you get a chance, go ahead and read these slides. This is starting at 3 on slide 17. Go ahead when you get a chance. You can look this over. Okay, thanks everybody. I'm going to step out for a little bit, and then I'll be back at 10:30 for office hours. So see you shortly. I'm going to